Welcome back. The objective of this video is to explore more compositions of functions. We'll also look at compositions of functions and how they relate to transformations of quadratics or graphs. And we'll also introduce inverse functions and how they relate to compositions of functions. So here in example 7, we've got a table of values for three functions, f, g, and h below. Find the values for each composite function given the operations below. So in example A, we want to find 2 times f of g of 2 plus 3 times g of h of 0. So going from left to right, I want to find g of 2. So I go over to 2, find g of 2, and I see that is negative 3. So 2 times negative 3, or 2 times f of negative 3, I beg your pardon, becomes 2 times f of negative 3. So now I need to put negative 3 into f, and I get an output of negative 4. So that becomes 2 times negative 4, which is negative 8, plus 3 times g of h of 0. So I need to put 0 into h, and I get an output of 3. So that's 3 times g of 3. I look for 3, and g of 3 is 2. So that becomes plus 3 times 2, or plus 6. So negative 8 plus 6 is negative 2. We'll do something similar in B, but now we're going to multiply. So we want to find g of negative 2, input negative 2 into g, and I get negative 1. So I want to find now h of negative 1. So I put negative 1, and I find my output of h, and I get 1.5, or 3/2. And I'm going to multiply that times f of g of 2. So I input 2, I find my output, and that would be negative 3, so times f of negative 3. And then negative 3, input that into f, I get an output of negative 4, so it's times negative 4, and negative 4 and 2 simplify to negative 2, and I get an answer of negative 6. In example C, we're given that function k of x is an absolute value function. It equals the absolute value of 3x minus 4. For what value of x is k of x equal to f of g of 0? So we need an output here, f of g of 0. That's going to be our output for k of x. So let's explore first what's f of g of 0. So we put 0 into our function, and we find the output there is 1. So we need f of g of 0 equals f of 1. So now I put 1 in, and I find that output is 4. So f of g of 0 is 4. So this now is equal to 4. So now k of x has to equal 4. So we'll say the absolute value of 3x minus 4 has to equal an output of 4. We're solving an absolute value function. So we'll separate this into 2. 3x minus 4 equals 4, or 3x minus 4 equals negative 4. That's how we simplify or solve absolute value equations. So we solve each one of these, and we get 3x equals 8, and x equals 8/3. And then we add 4 on this one. We get 3x equals 0, and x equals 0. This is an and. So we get x equals 8/3 and x equals 0. In example 8, we're going to describe the transformations of the composition of functions given below. So we've got f of x equals x squared. That's our generic Joe parabola with a vertex at the origin. G of x is x minus 1, and h of x is 2x. And we want to find f of g of x. So we're going to put g of x, or x minus 1, into f of x. So that yields y equals x minus 1 squared, which is a shift of f of x just 1 unit to the right. So we take that, we move our vertex over 1 right, and plot our points, 1 to the right, 1 up, 2 to the right, 4 up, and they're symmetrical points, and we can go ahead and graph that. That's just one Joe parabola shifted 1 unit to the right. In B, we want to find h of x, f of h of x, so we're going to take h of x, or 2x, and we're going to input it into f, or x squared, so we end up with the quantity 2x squared, which when simplified gets us 4x squared, which is a horizontal shrink. We're shrinking horizontally by a factor of 1/2. That's that reciprocal of 2. And our new graph is squeezed, so now we're graphing 4x squared. So it's really going to squeeze that graph. We're going up 4 times as high here, or a horizontal shrink by a factor of 1/2. So when x is 1, y is 4. When x is 2, y is 16. So that's going to be way up here. And so we've really squeezed this graph. Wow, I did not do a good job of graphing that guy. I totally whiffed on that point. Try that again. That's a little better. And then in C, we're going to take f of x and put it into g. So now our inner function is x squared, and our outer function is x minus 1. So now we have the quantity x squared minus 1. Now this is a shift up and down the y-axis. We're going to shift down just 1 unit. So we have a shift vertically 1 unit down, and there's our graph of y equals x squared minus 1. In example 9, we want to complete the table for values for f of x and g of x. Find the values for h of x, which is the composition of f of g of x. So let's start by inputting values for x and finding our outputs for f of x. And that's, I'm going to use the black graph because that's f of x. So when I input -4, I output -4. When I input -3, I output -2, and so forth. So I've completed the table for the black graph f of x. When I input -2, my y value is 0. When I input -1, my y value is 2, and so forth. G of x is the blue graph, and I can complete that pretty quickly. When I input -4 into g of x, I output 2. When I input -3 into g of x, I output 1. When I input -2, I output 0. When I input -1, I output -1. When I input 0, I output -2. When I input 1, I output, ooh, that's a little tricky, -3/2. And -1, -2 for an input of 3, and -3 for an input of 4. Now h of x, which I'll do in red, is a little bit sneakier. That's the composition of f of g of x. So let's take a look. When g of x outputs 2, that becomes my input for f to create h of x. So this 2 here is my output of g of x, which now is my input for f of x. So now that I have to input 2, which creates an output of 1. So h of x, my first value here, is 1. And then when g of x outputs 1, that becomes my input, and I have to see what I get for f of x, and that is 0. So my next value is 0. And then when g of x outputs 0, that becomes my input. And what's my output for f when I input 0? It is 1. So now I have to go to an input of -1, and it outputs 2. Input of -2 outputs 0. And input of -3/2 or -1.5, which we don't have. So I go to my graph, and an input of -1/2 or -1.5 on f of x gives us an output of 1. An input of -1 into f gives us an output of 2. An input of -2 into f gives us an output of 0. An input of -3 into f gives us an output of -2. So all my h of x values now I have listed. So in example C, it says graph, or part C, graph the points x, h of x on the blank grid. So I'm going to graph the x values of -x and the y values of the output of 1. So when I input -4, I output 1. When I input -3, I output 0. When I input -2, I output 1. When I input -1, I output 2. When I input 0, I output 0. Input 1, output 1. Input 2, output 2. Input 3, output 0. Input 4, output -2. And now I can string all those together. And we get a function that looks like this. In example 10, it says for each of the following, find f of g and g of f in the domain of f of g. Using a graphing utility to graph each composition function, determine whether f of g equals g of f. And if f of g equals g of f, we are going to learn later that those are then inverse functions of each other. So let's take a look at example A. F of x equals x cubed minus 1, and g of x equals the cube root of x plus 1. To find f of g, that means put g into f. So I've done that. I've taken the cube root of x plus 1 and put it in for x. So I've taken all this and I put it in there for x. So we get the cube root of x plus 1 cubed minus 1. Those are inverse operations, and we get x plus 1 minus 1, which is equal to x. And then I reverse it. We're going to do f of g of x. So we're going to take f of x and put it in for x into g. So the cube root of x cubed minus 1 plus 1. And simplifying the inside, we get the cube root of x cubed, which is simply x again. So our domain is all real numbers. And f of x is indeed equal to g of x, and g of x is equal to f of x. And repeating the process in example B, I'm inputting g of x into f of x. So we have 1/3 times the quantity 3x plus 3 minus 3. The quantity is important. The notation is important. Make sure you have that. And we get x plus 1 minus 3, which is equal to x minus 2. And reversing the process, inputting f of x into g. So now we're taking 1/3 x minus 3 and put it into 3 times the quantity x plus 3. So we get 3 times the quantity 1/3 x minus 3, which is x minus 9 plus 3, and that simplifies to x minus 6. So in B, those are not inverse operations. They asked for the domain of f of g of each, and I think they're both all real numbers. So there's an example. If we put these in our graphing utility, we could easily do that, and we'll take a look at that at class. And we'll get some more practice with this as well when I see you in class.